Hey everybody, this is the notes for section 2.2. In this module, we're doing 2.2 and 2.3. We'll be okay. So 2.2 is all about describing sets. Let's go. When we talk about a set is a well-defined collection of objects or elements or members. They call them all different things. Usually you call them elements of a set, but you'll also see it as members. When we say well-defined has a mathematical definition. What it means is it's clear whether or not something is in a set. So there's a rule that says these are the kinds of things in there, or these are the kinds of things that are not, or you can actually see what's in it, okay? So which of the following things are a set? Is interesting numbers a well-defined set? Oh, I get my pen. No, because your set and my set would be different, right? Or maybe there's nothing in your set, I don't know. But it's not like a concrete black and white kind of thing that we could figure out what's in or not. Multiples of 2, yes. Because we could actually write that out and write a rule for it. Good writers. Again, kind of an opinion, right? So nope. The current board of directors in Microsoft? Yes, right? There's people on the board. We could look it up. We know who they are. We could write our own names down on a list. Numbers that can be substituted for x so that 3x plus 18 equals 24. Well, sure, we can solve that equation. There's going to be one answer, and that one answer is going to be in the set. So yes, that's well defined, okay? All right, one important note here. When we talk in this section, uppercase letters are used to name a set, like set A, okay? Right, you see here. Lowercase letters are always going to be elements of the set, members, things inside of it. So you might have numbers, you might have letters, but if you see a capital letter, it's the name of a set, a group. If you see a lowercase letter, it's inside, more than likely. There are also some important symbols. This crazy looking E means something is an element of a set. So if you see that, we read it as is an element of. If you see that same E with the crazy line through it, it means it's not. So it's something is not an element of whatever set. So if I have set A, and it has 1, 2, 3, 4, 5 in it, and set B, I have A, B, C, D in there. I read this down here that says 1 is an element of set A. So now what are 2 elements in set B? And write them down, okay? So lowercase a is an element of set B. Sorry, again, writing with my finger, not so much. B is an element of set B. Okay, that's what that would look like. That's how you read that. The other thing I could say is that P is not an element of set B, okay, because it's not in its set up here. All right. There are 3 ways that we can write down a set. We could write it out in words, right? We could say this set has all multiples of 2. So we could say set A is multiples of 2. Okay? We could make a roster listing, and we're going to see that in a second. When we do a roster, basically what we do is we actually write the things out. So if I'm going to do multiples of 2, 2, 4, 6, 8, 10, 12, and then if I add those 3 little dots at the end, the ellipsis, it just says it keeps on going forever. So there's a roster. It's a listing. It's like a roster for a football team. It tells you who's on there. Set builder notation may or may not be new for you. Depends on what classes you've taken before this. So what we do in set builder notation is we write it as a rule, okay? So it's written like this. It starts with x, because we use a variable to describe a rule. It says x. This big long line here, we read as where x is, and we can at this point write is a multiple of 2, like in words if we wanted. But we could also write it as 2x. Okay, this would be a multiple of 2. Anything I multiplied by 2 would give me a multiple of 2. So write the following in roster form. So I want to write the list of what's included. This one, if we read set C, it says C is 2k plus 1, where k is equal to 3, 4, or 5. So now to figure this out, I just need to put 3, 4, and 5 in for k. So I'm going to make my bracket. Ooh, that's a terrible bracket. Apologies. All right, so now make a better bracket. If I put in 3 for k, 2 times 3 is 6, plus 1 is 7. If I put in 4 for k, 2 times 4 is 8, plus 1 is 9. Put in 5 for k, 2 times 5 is 10, plus 1 is 11. There is my roster. This one, D, says D is X where, X is a positive, even, natural number less than 8. So we have to take it apart. Okay, first, everything we put in this roster, in this set, has to be positive. They all have to be even also. And then the trick here is natural number, right? Do you remember what the natural numbers are? Natural numbers are numbers we can count on our fingers, literally. So we can't count 0 on our fingers. We can't count half on our fingers. We can't count, -3. Natural numbers start at 1 and count up by whole numbers. So 1, 2, 3, 4, 5, 6, 7, 8. So we need it to be positive, even, and natural. So let's see. I would start with 2, 4, 6, and then do I include 8? No, it's got to be less than 8. So there's our set. There's our roster. Okay. All right. When we say the word inclusive, it means that both ends of the list are included in a set. If you don't see that, you're going to assume that they're not. So for this example, it says set A is the set of natural numbers between 10 and 15. Remember, natural numbers are things we can count on our fingers. We can't count 10.2 on our fingers. So for this, we'd have 11, 12, 13, 14, between, okay? On the second part, set A is the set of natural numbers between 10 and 15, inclusive. That means my set changes because I include the ends. Oh, wow, I'm trying to write 15 because I'm thinking about it. 12, 13, 14, 15, okay? So the sets are different because of that word inclusive here. Okay. Two sets are equal when they have the same elements. The elements don't have to be in the same order. It's fine. But when two sets have exactly the same elements inside of them, they're equal. Okay? So are sets A and B equal? Well, let's see. 1, 1, 3, 3, 5, 5, 7, 7. They are. There's nothing in, they have exactly the same elements. So yes. An element of two sets, if the element of two sets, if the elements of two sets can be paired so that for each element of P, that's the first set, there is exactly one element of S. And for each element of S, the second set, there's exactly one element of P, then two sets, P and S, are said to be in one-to-one correspondence. So what does that actually mean? Well, I don't know. That means there are 3 people in 3 swimming lanes. How many matches are there? Well, we can make up a diagram, right? And if these are the pool lanes and these are the swimmers, I could put lane A, B, C. Swimmer 1, swimmer 2, swimmer 3 could go in lane A. Swimmer 1, swimmer 2, swimmer 3 could go in lane B. 1, 2, 3. Those are all the matches, right, that we could make here. Swimmer 1, swimmer 2, swimmer 3. It's not about how it actually would work, right? Because like once swimmer 1 goes in lane A, then there's no swimmer 1 in lane B. It's what's all the possibilities, okay? The other way to think about this is you can write them in pairs. A would be paired with 1, A could be paired with 2, A could be paired with 3, B could be paired with 1, and so on. You get the idea. So we would be making, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 3 people, 3 lanes. This is part of the fundamental accounting principle. So if event M, number of lanes, can occur in M ways, and event N can occur in N ways, then M followed by M followed by N can occur in M times N ways. So if we go back a slide, we had 3 things in set P, 3 things in set S. 3 times 3 gave us 9. Here, it says it's going to give us M times N. So there are 2 sets, it says, with 2 elements each. So let's pretend. Let's have set A have X and Y in it. We're going to have set B, and it's going to have 1 and 2 in it. Well, 2 elements, 2 sets. 2 times 2 should give me 4. So the number of one-to-one correspondences is 4, but we should actually see what that looks like. So we could do X and 1, X and 2. We could do Y and 1, and Y and 2. There's our 4. So you can see the matches. All right. Now, before we talked about equal sets. Equal set and equivalent sets are not the same, okay? 2 sets are equivalent, and this is how we write equivalent right here. The symbol for equivalence is this. If IFF is if and only if there exists one-to-one correspondence between the sets. Equivalent and equal are not the same when we talk about sets, okay? Equivalent is about how many can we match them one-to-one. Equal is about having the same stuff in them, okay? So let's test this out a little bit. So I have set A has PQRS. Set B has ABC. Set C has XYZ. And set D has BAC. Which sets are equal? Let's start there. Well, A doesn't have any overlap with anybody. B and D, right? Do you see it? They have exactly the same stuff in them. So B is equal to D. Are there any that are equivalent? Well, yes. If sets B and D also could be set up into one-to-one correspondence, the number of elements in there match. But B and C also have the same number of elements. You can one-to-one correspond them. So B and C are equivalent. C and D, also equivalent. They have the same number of sets. We could match them up, or same number of elements. So if 2 sets are equal, are they necessarily equivalent? Yes. Because if they were equal to start with, that means they've got the same amount of stuff in them, which makes them equivalent. If 2 sets are equivalent, are they equal? Well, no, we see that, right? B and C are equivalent. They can be matched in a one-to-one correspondence, but they're not equal. They don't have the same stuff in them. Okay. The cardinal number of a set. This is something that is going to come up on tests all semester long, and you are going to forget. So this is really important. This one makes me insane. Is denoted as N of A. That's how we say it. We want, and this reads as the number of elements in set A. This is when we're asking for the cardinal number. How many things are in that set? So here are our sets. I want to find N of A. Literally just count how many things. Well, in set A, there's 1, 2, 3 things. So the cardinal number of A is 3. For set B, there's 1, 2, 3, 4 people. So the cardinal number of B is 4. Set C, 1, 2, 3. The cardinal number of C is 3. That's all it is. It's just count them. okay? All right, this is also really, really important. When an empty set has no elements, or a set has nothing in it, it's called empty or it's called null. We can write that in two ways, okay? We can write it with a circle with a line through it, or as a set with nothing in it. What we cannot do is use them both at the same time. Basically, what this is saying is this is a set that includes an empty set. This is like taking an empty box and putting it in an empty closet. Once you put the box in the closet, it's not empty anymore. Okay, there doesn't need to be anything in the box, but now the closet holds the box. So this is an empty closet. This is an empty box. Separately, they're empty. Mush them together, it's got something inside. All right, another definition, a set is finite if it has nothing in it, or if we can actually count how many things are inside a set. If not, a set is infinite. So this is the difference between me saying like set A has 1, 2, 3. Okay, that's a finite set. Set B, I could say, oh gosh, that's a terrible bracket again, is 2, 4, 6, 8, 10. Remember those multiples of 2? Well, they just continue on. That's an infinite set. It grows and grows and grows. I could just keep counting. The universal set is sort of the overarching set that contains everything for any discussion of sets. You'll see this more in a little bit, particularly in the next section, but that's what it's called. It's sort of the universe of whatever math you're working on. All right. This is the other tricky thing in this section. So there is a subset. Set A is a subset of set B if every element in A is also in B. So when we write subset, this is how we write subset, okay? Suppose I have A, I have B, and I have C. Who's a subset of what? Okay, well, let's see. I know that every element inside set A is also in set B, isn't it? So A is a subset of B. I know that B, like the element B inside of set C, is also in set B. So C is a subset of set B. Additionally, the element B in set C is also in set A, right? So C is a subset of set A, okay? There is also something called a proper subset, okay? This is the tricky thing. This is how we write proper subset. It's just the same notation without the line underneath. The difference in the definition is that all of the elements of set A are elements of set B, and A and B can't be equivalent. So this didn't cause us a problem here. Technically, though, C is a subset of B. They have all the same things, right? This says that it's only proper if the things aren't equivalent. So if set A is equal to set B, that means it's called an improper subset. The only thing that we can say at that point is that it is a subset, just not a proper one, okay? Oh, that should be a subset spelling. The only improper subset when we're writing subsets is the set itself, okay? All right. If A is a subset of B and B is a subset of A, then they must match, okay? They must be equal. If every element of A, like I said a minute ago, is an element of A is a subset of A, but it is not a proper subset. It would not be okay to write this because they're equivalent, or sorry, they're equal. When we list out subsets, The one we will always forget is the empty set. I can think of it like a closet. I have a closet full of clothes. I can make outfits, right? I can pull out pants and shirts and whatever. I could wear them all at once. That's an improper subset. I could wear a couple things at a time. Those are all subsets and proper subsets. Or I can take everything out and have an empty closet. That's one of the options, right? All right, so let's find all of the subsets. So if we have set C and set C has A, B, and C in it, we need to think about what all the choices are here. So it can be a subset of itself. But note this is improper. I could also have just a couple of things, right? If these are all the things in my closet, I could wear them all. That would be kind of crazy. Or I could wear just a couple of things. Maybe I only need thing A. Maybe I only need B. Maybe I only need C. Maybe it's freezing out and I need a little more, so I could do A and B, or A and C, or B and C, okay? Or I could decide I need to go shopping and not use anything from that set and have it be the empty set, okay? That's all of the options. So for this set C, there's 1, 2, 3, 4, 5, 6, 7, 8 subsets. But only 7 of them, remember, are proper subsets. Because that set where I wore everything, that's silly. It's improper. A set containing 3 elements has 8 subsets. To figure out how many subsets something has, and that's really handy, you have 2 to the n, where n is the number of elements. We had 3 elements in our set, so 2 to the 3rd gets me 8. To figure out the number of proper subsets, we always have to take that one out, that one that exactly matched, that was equal. So 2 to the n, 2 to the 3, minus 1 gets me that 7. The only improper subset is the set itself, remember. All right, so I have set A, 1, 3, 5, 7. I have set B, 3, 7, 5, 1. Which is correct? Are they both correct or neither? Is A a subset of B, or is A a proper subset of B? Well, can't be proper, right? They are equal. So it is a subset, but it is not a proper subset. All right, so this is the end of the notes for 2.3. Or sorry, excuse me, 2.2. We're going to move on to the notes for 2.3. That's going to be in a separate recording. Okay, this section will have 2 separate documents for the completed notes, one for each of these sections. Okay. All right, I'm going to stop this one here. I'll see you in 2.3.